Now that we have discussed the most important design considerations for a crystalline silicon solar cell, we will look at how industry and research institutes have implemented these features to produce record efficiency solar cells. In this video, we will show the ideal solar cell design based on the features mentioned in previous videos, such as surface texturing, passivation and localized doping. Next, we will move our focus to advanced concepts for solar cells based on crystalline silicon that deviate from the standard solar cell design. Note that many different design concepts for crystalline silicon-based solar cells have been published in literature, and in this video we cannot discuss them all, but we have selected some interesting concepts for you that are now researched and produced. In this video we will discuss the series of passivated emitter and rear solar cells, starting with the PERC, the passivated emitter rear contact cell. Secondly, the PEARL or passivated emitter rear locally diffuse cell, and finally PERT or passivated emitter rear totally diffuse solar cell. But first, we will look at the overview of the achieved conversion efficiency over the years for crystalline silicon-based solar cell technology. In the United States, the National Renewable Energy Laboratory, abbreviated to NREL, keeps track of the record conversion efficiencies for all solar cell technologies. In this graph from early 2017, we see that the record efficiency for a crystalline silicon solar cell under one sun illumination is 26.6%. This particular cell will be discussed in the next video, but how far are we from the maximum theoretical conversion efficiency? The conversion efficiency of silicon-based solar cells, according to the Shockley-Queisser limit, is just above 30% for terrestrial applications. A recent study of Richter et al. In 2013 further elaborates on this limit and concludes that the theoretical limit is somewhat lower at 29.4%. This lower efficiency limit is obtained by taking into account Auger recombination rather than radiative recombination only, as is done for the Shockley-Queisser limit. In particular, in an indirect bandgap material as crystalline silicon, the Auger recombination mechanism is important and should be taken into account. To achieve this limit, the crystalline silicon wafer should be intrinsic and should have an optimal thickness of 110 micrometers. Now we know the theoretical maximal conversion efficiency, we will look at three different ways how the industry has implemented the design considerations that have been discussed in the previous videos to obtain really high efficiency solar cells. Here we see the conventional solar cell design that was used in the early 1980s. Notice that this design did not yet include a selective emitter and back surface field. Researchers focused mainly on improving the front surface of the solar cell by passivation and texturing. In 1983, researchers at the University of New South Wales in Australia started developing the PERC technology. This design features a thermal oxide passivation layer between the silicon back and the metallization, with small areas in the oxide for the metal to contact the silicon semiconductor. Evidently, in this design, the contact area between the metal and semiconductor is reduced substantially. The conventional solar cell has been developed further to include a back surface field, or BSF, realized by the diffusion of aluminium, a p-type dopant in silicon, after the back contact has been deposited onto the wafer. Also, the PERC design from the early 1980s has been developed further, and at this moment the most produced crystalline silicon solar cell is a multi-crystalline silicon cell with PERC technology. In addition to the PERC technology, with the oxide passivation layer at the back, the current design may feature a selective emitter and a local BSF around the holes in the oxide. And also this is realized by diffusion of aluminium after back contact deposition. Trina Solar holds the current record efficiency of 21.3% using some of these features. The PERC technology was further developed as there was still a lot of potential by improving the backside of the cell. This resulted in the PEARL technology in the late 1990s. At the end of the last century, the PEARL solar cell was introduced as a high-efficiency concept solar cell. PEARL is the acronym for Passivated Emitter Rear Locally Diffused. As we can tell from this illustration, this design includes all the considerations that have been discussed in the previous videos. The front surface is textured with inverted pyramids and coated with a double-layer anti-reflective coating to reduce reflection. Using 2 layers for anti-reflection coating allows to make the transition in the refractive index even smoother, reducing the reflection even more. Secondly, the surface of the P-type wafer is passivated with an oxide layer to reduce surface recombination. The highest purity grade float zone wafer has been used to reduce bulk recombination. And a very fine front metallization is deposited using photolithography to reduce the coverage of the front surface and thereby shading losses, leading to an increased short circuit current density. On top of that, the fine metallization grid results in an increase of the fill factor. Finally, the metal semiconductor interfaces feature locally increased doping to create a selective emitter at the front contact and a local back surface field or BSF at the back contact. The highly doped P-type region that creates the back surface field is in this case obtained by boron diffusion that was patterned on the cells before applying a metal contact. Combining all these features, the researchers managed to obtain a conversion efficiency up to 25%, which remained unchallenged for more than a decade. The PEARL concept, however, includes some complex processing like photolithography that are therefore hard to scale up and are expensive. It also suffers from current crowding effects since there is only local diffusion at the back contact. Holes will need to travel laterally towards the doped regions in order to be collected, which increases the cell's series resistance. PERT technology focuses on this specific issue. PERT is the acronym for Passivated Emitter Rear Totally Diffused. The difference with the PEARL technology is that the rear now has a full area back surface field by moderate doping. This improves charge carrier conduction towards the heavy doped areas and ultimately reduces the series resistance of the cell. This technology is most commonly implemented on an N-type doped wafer base, argued by the higher minority carrier lifetimes, reduced sensitivity to light-induced degradation, and a more easy thermal oxide passivation compared to a P-type wafer base. To conclude this video, the PERC technology improved the passivation at the backside of the solar cell and is now the most produced solar cell on multicrystalline silicon. We have seen that derived from the PERC design, the PEARL was developed using relatively expensive production methods. This resulted in a record efficiency of 25% in the late 1990s. Finally, the PERT solar cell improves the current transport and lowers the series resistance by total diffusion of the back surface.